Welcome to clickmyproject.com. This video demo is about an image processing concept about color constancy for multiple light sources. Color constancy algorithms are generally based on the simplifying assumption that the spectral distribution of a light source is uniform across scenes. However, in reality, this assumption is often violated due to the presence of multiple light sources. In this paper, we present a methodology that enables color constancy under multiple light sources. Methodology is designed according to the following criteria. It should be able to deal with scenes containing multiple light sources. It should work on a single image. No human intervention is required, and no prior knowledge or restriction on the spectral distribution of the light sources is required. Although the proposed framework is designed to handle multiple light sources, the focus in this paper is on scenes captured under one or two distinct light sources. Furthermore, not only images recorded under multiple light sources, but also images that are recorded under only one light source is properly processed. To construct color constant images from scenes that are recorded under multiple sources, the proposed methodology makes use of local image patches rather than the entire image. These image patches are assumed to have uniform spectral illumination and can be selected by any sampling method. In this paper, grid-based sampling, key point-based sampling, and segmentation-based sampling are evaluated. After sampling of the patches, illuminant estimation techniques are applied to obtain local illuminant estimates, and these estimates are combined into more robust estimations. This combination of local estimates is done with two different approaches, that is clustering and segmentation. The first approach is to cluster the illuminant estimates, taking the cluster centers as final illuminant estimates for each of the regions. The second approach is to take spatial relations between local estimates into account by applying segmentation on the back projected local illuminant estimations. Finally, when the resulting illuminant is estimated, a modified diagonal transform is applied to obtain the color corrected images. Project flow starts with sampling. The first step is to sample patches from the image. For each patch, estimation is computed of the light source valid for that patch. Different sampling strategies can be used: grid sampling, key point sampling, segmentation sampling. Grid-based sampling has the advantage that patches contain varied information, whereas patches that are selected using segmentation-based sampling will generally contain similar colors. Finally, key point sampling is specifically suited for edge-based color constancy methods, as the key points are located around edges and junctions. In this paper, key points are located using Harris detector at multiple scales. Step 2. Patch-based illuminant estimation. As the illuminant for each patch is assumed to be spectrally uniform, traditional color constancy methods are applied on every patch to estimate the local illuminant. Color constancy is applied on each patch, resulting in one estimate of the illuminant chromaticity per patch. Combination of estimates. Step 3. Since there is only a limited amount of information available when using a relatively small patch for the estimation of light source. This may introduce estimation error. To overcome this lack of information, patches that are taken from parts of the image that are illuminated by the same light source are combined to form a larger patch. Patches that are illuminated by the same light source are likely to vote for the same illuminant. Assuming that the number of clusters is known, we assume the chromacity can be grouped together using any clustering algorithm. Step 4. Backpropagation of clusters. After the different estimates are grouped together into groups, the result can be back projected onto the original image to identify the locations of the image that are illuminated by each of the estimated light source. This results in an illuminant classification where every pixel is assigned to one of the estimated light sources. After back projection, a pixel-wise illuminant estimate is obtained. Step 5. Color correction. Finally, using the pixel-wise estimates, the output image is constructed. Transforming the input image so that it appears to be taken under a white light source is an instantiation of chromatic adaptation. Many methods to do this exist, but all assume that the color of the light source in the input image is known. Now we'll see the demo of this project. To execute, right-click on mainfile.m and select Run File. Select Input Image. Select any image from the dataset folder. Here I select Input Image 2 and click Open button. The selected image gets displayed in the first axis. I do grid-based sampling, that is, I divide the input image into n cross n blocks. I have resized it so that I can divide it into n cross n patches. Key point based sampling. This process takes time as it has to identify the key points. This is the output of Harris detector key point based sampling. Segmentation based sampling. This also takes time as it has to identify the regions. This is the output of segmentation based sampling. It has identified the different regions with different illuminations. Patch based estimation. The mean and the max color difference for grid based sampling, key point based sampling and segmentation based sampling are calculated here, and the local luminance of patches is estimated here. Estimate of combination. Here we can see the spectral distribution of light sources being represented. This is the actual coverage of our image and the target coverage of the image to be achieved. These are the luminance versus wavelength graphs of the original image. Then this is for grid based sampling, this is for key based sampling, and this is for segmentation based sampling. Then the next step is we have divided clustered grid based sampling, key point based sampling and segmentation based sampling data points into lesser number of clusters. Here we have grouped into 3. We do back propagation. Here we get the back projection output, and here the filtered back projection output. These are the luminant classification values. And finally, color correction. This is the gray world method, white patch, general gray world, first order gray edge and second order gray edge method. Here this second axis shows the gray world method. Thank you.